and welcome to our latest episode of Explaining Our Agentic Future. I've actually said that enough times now that I actually remember the title to my own podcast, which means it's time probably to change it so I won't remember it again. We've done some interesting episodes lately talking about AI with legal knowledge graphs, and we're joined today with people that are also in the knowledge graph space, but kind of approach it from a different direction. And they're from FalkorDB, and we're joined today with Roi and Dan. Thank you for joining us today, and please introduce yourselves and what you do at FalkorDB.
Thank you, Daniel. So, yeah, I'm Roi Lipman. I am the co-founder and CDO of FalkorDB. We will get into in more details what exactly Falco is doing, but just to put it out there, we are developing a low latency, high throughput graph database, which you can also use for your knowledge graph and GraphRAG use case.
Okay. How about, and we also have Dan with us today.
Yeah, nice to meet you, Daniel. So my name's Dan. I'm part of Roi's team. I run marketing efforts at FalkorDB. And actually, I'm the one that's tried to set up today's podcast, and we're very excited to be part of the show.
And you're the one I can see with the cool T-shirt already.
Yeah, exactly. It's part of what I'm hoping maybe we'll touch on today, but we're not sure. It's just the what we put together for the community that we're trying to put together of developers who are experimenting with retrieval augmented generation and are into performance. So.
Yeah, that's an interesting one too, is, I kind of have, I wonder how long we're going to be using that term RAG. The term GraphRAG is not really kind of sort of caught on, is not really all that commonly used, I guess because of Microsoft kind of laid claim to that term. So
yeah.
it's interesting. People were proposing using hybrid RAG for a while, but I don't know how much longer that term is going to be used. So that's an interesting point in and of itself. The thing I normally like to start out with, especially when we talk to people with so much knowledge about knowledge graphs or knowledge graph structures, is I find that knowledge graphs are a bit of an unusual pick, or I guess they're not anymore. And I have a very unusual way of learning about knowledge graphs. So I was always curious how other people ended up in the world of knowledge graphs.
Yeah, sure. I mean, the term knowledge graph might be a specific angle or the way in which you perceive a graph structure. Usually people, or that's the way I think about it, is knowledge graph is a graph that captures facts. For example, I'm participating in your podcast, so you might capture this in a graph format where we would have ourselves represented as entities, nodes in the graph, and then there would be a link or an edge connecting myself to your entity saying that I've been hosted on your show. And then there might be another link from you to your podcast saying that you are running the podcast. So knowledge graphs are kind of being revived. It's at least a 10-year type of an idea, which now with the booming of Gen AI and RAG solutions is kind of blooming again. But in addition to just knowledge graph, there's the maybe classical, or there are so many different use cases for graphs. And the way that I've kind of been introduced to the graph world is because I took a course during my studies which dealt specifically with graphs and graph structures. And I was just, fascinated by this abstract idea, which is extremely, simple to comprehend. The way, that you can think about data being modeled or represented as a graph. And then when you're making this mental transition from the domain in which you're in or the problem that you're facing, if you are able to think about this in graph terms, then a whole world of approaches, solutions opens up to you. And I like this transition, taking a problem from one domain, abstracting it, and then gaining all of this extra knowledge, abstraction, tools that you can work with to try and solve the problem. So I really enjoyed that course, and I knew that I wanted to be dealing with graphs. And that was about 10 years ago. And I've been doing graphs intensely for the past 8 years now.
So this has really been a focus of yours for quite a long time in your career. I mean, because like I say, I'm a bit of the opposite. I backed into this after 20 years of doing things that seemingly have absolutely no connection whatsoever. And I found that knowledge graphs tend to be a very interesting information structure for, as you said, connecting disconnected concepts and ideas. And I suspect that there's some sort of deep personal yearning for connection that may be what's attracted me to knowledge graphs. But that being said, one of the things I think is really interesting about FalkorDB, and I'd love to hear more about its genesis, and we're going to talk a little bit about some of the decisions you've made. Is that you're taking a different approach in that how you actually store information. We think of when we think of knowledge graph, we primarily think of text, and that's why we look to knowledge graphs and be this way to structure text. But FalkorDB, underneath that text, is actually storing relationships and structure in a very different way. Can you talk about that?
Sure. Yeah, that's the way that we go about representing graphs and traversing them, or doing analytical type of task on them, is a bit unique in our industry. Usually when people are thinking about graph representation in memory or on disk, usually adjacency lists or linked lists come up. And I think that the main reason for that is that most textbooks, whenever they're talking or describing graphs or graph algorithms, they would turn into this data structure to present the different ideas and those algorithms. I think that's probably because it's easy to comprehend, it's easy to implement, and so that's what usually you would find out. But there are some cons, specifically, on the performance aspect of it that comes along with it. What FalkorDB is trying to do is to give a really high-performant graph database, and the way that we go about this is by using sparse matrices and sparse linear algebra to represent our graphs and to traverse them or to run different graph algorithms on top of them. And so the basic idea with matrix representation of graphs is you can think about the matrix as a rectangle where you have rows and columns. And usually what you would do is that you would associate the row indices or an index with a node. So each node has a unique ID representing it, and then you can trace the node or associate the row with a row index and a column index. And let's say that I'm represented by node with ID 1. You're represented with node with ID 2. And so if we want to represent the connection between myself and you, then we would have a matrix where at row number 1, column number 2, there would be usually a Boolean true value in that entry. And so this is how you can capture the overall topology of a graph in a matrix. Now, what's interesting is that usually graphs that are naturally formed, they tend to be sparse, meaning that the number of actual relations or edges in the graph is extremely small compared to the potential number of connections. So if we have a graph with n nodes, then each one of those n nodes can have n-1 edges connecting itself to every other node in the graph. That's a full mesh, but usually that's not the case. And so what we do, we take advantage of this sparsity element, and that's been utilized by the sparse matrices. And so I should mention that the mathematical aspect is all being taken care of, or mostly being taken care of, by a library called GraphBLAS. So if our audience is familiar with BLAS, which is a mathematical library for doing linear algebra, more specifically, for the most part, this is dense linear algebra, meaning that every entity in the matrix has, representation. GraphBLAS is a sparse version of BLAS, dealing with both sparse matrices and sparse vectors, and giving you the ability to run all sort of different operations on those elements, like matrix multiplication, or addition, transpose, a lot of variety of different operations that you can run on those elements in GraphBLAS. And so what this gives Falkor is, first, a low memory footprint, because those matrices and vectors are highly efficient in terms of memory consumption. And second, very high hardware utilization, and really high performance when it comes to traversing the graph or running different graph algorithms.
Right. I'd looked into GraphBLAS a little bit, and we have links down below for anybody that's interested in learning more about GraphBLAS. And in case anybody's a little bit confused about these sparse matrices, just think about a matrix again, which is just like you said, a rectangle of numbers. And it's sparse because most of the values end up being 0. And one of the things I found interesting is that if you have these very large tables, these very large matrices, and you still have to store the value 0. But my understanding is that there's a way that you don't have to store the value 0, and that's where a lot of your efficiencies come in. Can you explain that a little bit?
Right. You can think about a Boolean matrix, or a Boolean sparse matrix, where every entry has basically 2 values, true or false. And you can think about true representing that, yes, there is a connection, and false saying, no, there's no connection. But with sparse, this Boolean type becomes a trinary operation, or a trinary value. You can choose, do you want the entry to hold the value true? This is first one. The second one is entry ij has a false value in it, or the third option is there's no data in that entry, so it's missing. And the way that sparse matrices take advantage of that in terms of memory consumption is via the actual implementation of the data structure. And so there are different formats to represent sparse matrices. The most common ones, I would say, are CSS, I believe, and CRS. It's compressed sparse row and compressed sparse column. And there are others, basically with CSR and CSE, the matrix is represented by a hierarchy of 3 arrays. Usually you would have an array representing the row indices, and then the second one in the hierarchy is the column indices, and lastly, you would have the values. With CSR, the first array would contain every entry for every row, whether or not there are some values in a specific row or not. Then for each row, you would have a pointer to the next array in the hierarchy. That would be the columns. And then you would have one entry for every value. And the same thing goes for the actual values array. And so you're just containing information for the most part for existing entries. Non-existing entries just are not present. So there is no memory being used to represent those. And it goes even further. In case the matrix is hypersparse, there are additional ways to compact this even further. If the matrix has only just a single value, for example, if you're dealing with a Boolean matrix where all of the entries in the matrix are true, then there is this optimization in GraphBLAS called ISO value, which means that this value array, which usually is of size number of active entries in the matrix, becomes just a single value. So what's the value at entry ij? If the entry is present, you look up the ISO value. Oh, it's true. And everybody's sharing the same true value up until the point where you're mixing or entering a false, and then it's no longer ISO. And then you would pay the price for keeping track of which entry is true or which entry is false.
And while I find all of this math behind the scenes fascinating, I suspect there's a lot of knowledge graph users who are thinking, well, this is really interesting, but I still have to work with the graph. And you have people that are, well, it seems like Cypher has really become the most common way of working with graphs now. And I wonder, well, how do you connect Cypher to all these mathematical representations? That sounds like that'd be quite challenging in and of itself.
Right. So I do agree with you. Cypher is becoming the most predominant query language for graphs, although the GQL query language, which is now a standard, had been published. And I think that eventually vendors would transition to GQL, which is extremely similar to Cypher in terms of how the query language looks and its abilities. But for the most part, I think it's Cypher. And I think there's
I know Nebula Graph and Neo4j are both very bullish on GQL.
Right. Yeah, I think that at least Neo4j participated in the ISO committee. Regardless, I think that picking or using one of the more popular query languages has the benefit of having LLMs being familiar with the language and LLMs being able to produce Cypher for a given question given in natural language. So it's important today that LLMs would be familiar with the query language that you are using. Now, in terms of how we process Cypher, then first and foremost, yes, we do are compatible, or we're supporting the Cypher query language. And the way that we're processing it is we're basically translating the patterns that are specified. For example, a pattern could be find all nodes that are reachable on some path going from A through some edge to maybe another node B, and then continue on this path until we reach the desired node. So there's this path being defined, And so what we're doing, we're looking at this path and we're converting it into a set of linear algebra operations. This is, for the most part, this is matrix-matrix multiplication, maybe some transpose, depending on the direction of the path. And I think that the key idea to take here is that you can traverse a graph represented via a matrix or a set of matrices by doing matrix-matrix multiplication. And this, I mean, this idea, the first time that I heard about it, about maybe 9 years ago, it blew my mind. So first, the fact that you can represent a graph via matrix, this is nice. But then, you know, when someone tells you, hey, listen, you can actually move through the graph by doing matrix-matrix multiplication, for me, it was fascinating. And that's the key idea that we build on. So you give us a path that you want to traverse. We translate that to operations on matrices, and we just evaluate that expression, and we end up with the desired nodes or edges.
And I find that absolutely fascinating, this idea that we're now representing knowledge, which we think of as text, and how we would typically represent them in relational databases, columnar databases, and you need these query languages to basically do, you know, does the query match this value? And now we're talking about, can we actually use linear algebraic techniques to do this mapping for us in a very different way? And then I start to think, and I bet a lot of other people in the AI space are starting to think, or hearing this conversation and thinking, well, wait a minute, isn't that pretty similar to what a vector database does, where we take text and we encode it in some of this numerical representation, and now we store it in these kind of matrix-like structures. I guess at the end of the day, these are all like these huge sets of vector spaces, and we're doing these calculations on them now. And when I hear this, I would love to get your thoughts on, are these two structures kind of converging, or how similar are they, or are there like key dissimilarities that there are a difference in approach?
Yeah. So let me start by saying that one of the most popular algorithms that you would find with vector databases is HNSW, which is a search type of a system where you're trying to find the most similar vectors in your database to a given query vector. And the way that HNSW goes about this is it builds a graph, a hierarchical graph, which you would start at the very top, which is pretty sparse. You would find one vector, which is the closest, usually the closest vector for the query one. And then that node that you've found on the top of the hierarchy would lead you to the next level, which is less sparse, and then the process repeats itself up until the bottom layer, in which you would end up with k vectors that are the most, or at least close enough to the query vector. So there are also graphs in the way that vector databases work, but in terms of the actual storage, I'm not familiar, but I can think about the way that vector databases might store all of those vectors. They might combine them into a single matrix. They might keep them separated, but I mean, matrices would show up all over the place in different domains. It's the what is actually being represented by the matrix that matters. For us, we are storing the graph topology. For vector databases, maybe they are combining all of those vectors that they have into a matrix, but they would probably work with dense matrices where sparse So the elements might show up, but for different reasons.
So what I keep hearing, and I've had this conversation with a lot of people lately, is a lot of the algorithms that are performing the calculations, that are performing the comparisons are very similar. So the thing that I keep hearing about when we think about performance, and I know especially for FalkorDB, you're really focusing on latency, how quickly can you extract information from your structure? Is the bottleneck for all that really is it really tied to how you're storing the information and the very nuts and bolts, the mechanics of that? It's not these elegant mathematical techniques, it's just how you store it?
I think that for the majority part, it's a combination of different variables. When you're thinking about the latency of processing a single query. So usually you need to get the execution plan right, meaning that whenever a database is faced with a query, the database would build something that is known as an execution plan. Basically, it's a set of steps that the database would need to run in order to produce the right result. And there could be different execution plans which would give you the same result, but the overall runtime of each plan differs. And you really want to produce the right execution plan for the given query. So if you're messing up this part, you can usually throw performance out of the window. But let's say that you've managed to build a performant execution plan for a given query. Now, with Graph, it's a lot about traversing. And if, for example, each time that you traverse a single node, for example, with adjacency lists and linked lists, you're accessing memory randomly. So every time you're accessing a different memory allocation in terms of address spaces, or if you need to go fetch some data from disk, then you're gonna really hurt your performance. With FalkorDB or with this sparse matrix approach, all of the data is laid out continuously. So usually memory access is very performant. Next up, when we're doing traversal, we're able to do multi-source BFS, meaning that we can, in parallel, traverse a graph from multiple sources and spread out. And lastly, maybe, is that traversing via matrix multiplication can easily take advantage of multi-threading. And so that what GraphBLAS does, it is basically doing for us, it's basically doing multi-source BFS in parallel. And the memory access is fantastic. And so this is one area from which performance is coming from. Thanks to the right decision with the data structures.
And that kind of brings me to something we alluded to a little bit earlier, and that when we talk about the fact that we're able to encode these relationships in mathematical representation. And I also think that we overlook that the language we're speaking right now, is also an encoding for concepts. And there's multiple layers of abstraction here. And one of the things I find fascinating is that it seems like mathematics is that a more direct way of representing these relationships? Is there a way to take language out of the equation and just represent this with mathematical structures? And I know this is something I think about a lot because of some of the work that I've done in the past, and seeing how all these things represent together, especially with vector databases. Again, we take text and we create this embedding, which is all of a sudden just a number. and we can put it in this set of other numbers. And it seems like there's some sort of meaning there. And as somebody who gives a lot of thought, I can tell, to information theory, is there something there in that? Is there some way of is math the universal language here for representing this, or are we just still not there yet? Are we still uncovering this? Is that something you ever think about?
It does bother my my mind. I think the lack of explainability is disturbing. And that's something that comes up with vector databases. We do understand the concept of how does the system works, but why does a sentence, a word, or a paragraph ended up with this specific vector representation? I think this is still unknown to us. And I think it would be, I know that there's research going on trying to really figure out what's going on within those models, embedding models. It's important, to keep on hammering this and try and figure it out what's going on there. I think that if we were able to do that, then new avenues would open up. So yes, it does disturb me, but with knowledge graph explainability is much easier. When you're running a query, when you're asking a question and you're not getting the right answer from an LLM or a RAG type of a system, you can actually look at the data and reason about it, because the data is meaningful. You're looking at nodes that represents ideas, and you're looking at the relationship between them, or you're looking at the Cypher query that might have been auto-generated by an LLM, and you can reason about the entire RAG system end to end. Not something that you can usually do with vectors, and I'm not here to hammer about vector RAG. Yeah, I think it's what you've mentioned is one of the big questions in academia, and I know that people are working on it to get better understanding on how, what exactly is happening within those modules, because at the end of the day, this is once again linear algebra, matrices being multiplied, and we are working in vector spaces and with embeddings at the end of the day.
And I think that it's also important to think that the language models themselves, when you dive into them, we're talking about very similar mathematics that's governing them. And one of the reasons I like to think about this problem is I think, is that the next step? Is that these architectures and these structures, do we start borrowing from each one? Some of the principles that you're using for FalkorDB and how you're connecting knowledge. Do we start taking some of those principles and do we introduce that to transformer architecture? Or is there a way of storing embeddings in the knowledge graph type structure and start to be able to do the same sort of calculations in the same type? And is that where we're going over the next couple of years, is combining all of these into one structure? Or is it a structure kind of like, I don't know, what we've done with TrustGraph, where we built an infrastructure, a system that connects them all together with some services that kind of manage those relationships? And I don't have a crystal ball. I don't know which one of those we go back and forth on which way is the answer ourselves.
So what I believe would be the leading solution to RAG systems is a hybrid type of a solution, which combines the best of knowledge graphs and vector or semantic search. And with the entire industry coming to this realization, or the entire industry understanding the value with semantic search, you see vendors from the wide range implementing vector indexing within their products. So you see relational databases, document stores, knowledge graph databases, they all roll out the semantic search capabilities. And so FalkorDB, like the majority of the vendors, has a built-in vector index. And so the idea behind this is to say, I'm not exactly sure which nodes I want to start traversing from. Let me do a semantic search, which would give me a set of nodes that are semantically similar to maybe a question, and let me traverse further from there. So it's a hybrid type of a system that utilizes both. I don't see at the moment incorporating LLMs into a database. That's not what I'm seeing, but we are looking or starting to look into GNNs, so graph neural networks, because we see good value in those performing predictions and categorizations of graphs. And this is, we're making our baby steps there, but we want to see FalkorDB because of our unique graph representation. If we can take advantage of that and maybe incorporate the GNN models into the database, or to expose the matrices as they are as an input to those GNNs, I'm still not convinced, but we would have to do more research on that. That's another direction in which maybe those matrices and vectors could show up, and the integration would be a little bit more smoother.
And what you're talking about with the hybrid approach is exactly how we've been approaching it with TrustGraph. And we're just now integrating FalkorDB into TrustGraph. We're testing that right now. And I'm really, really interested to see how that compares and contrasts. And I think that's really interesting, maybe being able to get all that performance out of one structure, because right now we've been having a separate knowledge graph structure and a separate vector database structure, but being able to do that all in one is a really, really interesting performance optimization that we're looking into. That being said, I know we don't have too much more time. I know you're very busy multiplying matrices together, which is a noble effort, by the way. I spent over a year of my life doing this for quantum photonic systems, which is, again, I could derail the conversation very quickly talking about this philosophical question: is linear algebra the grand unifying structure for information and quantum? And I won't derail us right now, but where do you see us going in this space? We talked a little bit earlier about, is the term RAG here to say? It doesn't seem like the term GraphRAG caught on. Hybrid RAG, I don't see as much as either. But if you just say RAG, people mostly think semantic search. It seems like you think that, and we're seeing this as well, that most all structures are going to start implementing semantic search into their products. So for 2025, where do you think we're going with this? And do you think there's going to be any really big disruptions in how we go about solving these problems?
Yeah, I do think that a lot of effort on pushing GraphRAG, this is where the focus is going to be. And I think that people had tried the classical RAG approach, and for the most part, or this is what we're hearing, users are not too happy with the overall accuracy of the systems. And so now everybody's turning to find a different solution which would yield better accuracy. And from a number of POCs that we have done, I can tell you that indeed, by building the right knowledge graph, we were able to achieve higher accuracy. I would say the accuracy had gone up from around 60% to around 85, 87% with the set of questions that those prospects and customers were interested in. But there are a number of big hurdles to overcome before, we can easily roll out GraphRAG solutions. And I think that the biggest hurdle is with knowledge graph construction. Now, there are usually two options, or the way that you would kickstart this process is if you have your data already in a structured format. This could be CSV, JSON files. Maybe you have your data in some type of a database, and you just want to make the transition from where you're currently at into graph, then the transition is quite easy. Things get more complicated when you're dealing with unstructured data. And so with that, usually what we do, and this is what we see the industry does, is defining a concise ontology, basically saying, these are the type of relationships and entities and attributes that I care about. They reside within my data, along with additional data that I maybe don't care about or don't want to see in my knowledge graphs. And so once you have this ontology constructed, then it's either working with LLMs, maybe fine-tuned models for entity extraction and finding the relationships with, within the data, or trying to apply some NLP algorithms or NLP approaches to try and find the entities and relationships within your unstructured data. So this is a big challenge, constructing a knowledge graph which actually captures all of the data that you care about. Next up is the actual querying and retrieval of the context. This is also done with LLMs, guided by the ontology. So basically, we're giving access to our knowledge graph to an LLM, saying, you have access to a knowledge graph, you can send out Cypher queries to it and know that this is the ontology that you're working with. So the LLM should have a good understanding what data is available to it within the graph, or what's not, what's missing. And so the LLM would be able to produce the right Cypher query given a user question.
I do want to end with saying that it's amazing that, everything that you're describing for the most part is so similar to the approach that Mark and I took with TrustGraph. So I'm gonna chalk that up to saying, great minds think alike, and that's obviously what's going on here. And we could go on. I mean, I honestly could. I could talk about this subject of information theory and using linear algebra to model it for hours. But I think you're far too busy building FalkorDB for that. And I want to thank you for taking the time to speak with us today. And I really hope this is a very different way of looking at knowledge and representations and even vector search, and giving people a lot to think about for where this space is going to go in 2025.